of columns. So his contribution is major in finding out the theoretical and experimental investigation of columns. Engineering literature is filled with formulas developed for an ideal column conditions, but these conditions are not encountered in actual practice. Consequently, a practical column design is based on primarily on formulas that have been developed to fit with a reasonable accuracy and test costs. What does it say is that in practical columns, it will have some imperfections. It will not be exactly like a theoretical columns. So whatever the conditions we are assuming for ideal columns, with that we are formulating the formulas, right? That conditions are not encountered in actual practice. The reasoning behind this procedure is simple, that independent derivation of column expression does not produce formulas that give results which compare closely with the test result curves for all slenderness ratios. So let us see this kind of testing of columns with various slenderness ratios. Okay. Here you could see about the material Pu by A, that's the stress at failure, and test result curve with respect to slenderness ratio. So slenderness ratio, if it is increasing, the Pu by A at failure is decreasing like this. So if the slenderness ratio is increasing, the stress or failure, it comes down quite drastically. So these are the test result curves. So what does it say? That testing of columns with various slenderness ratios result in a scatter range of values, such as those shown by broad band of dots. The dots will not fall on a smooth curve, even if all the testing is done in the same laboratory, because of the difficulty of exactly centering the loads. Now you understand, like, because of the difficulty in exactly centering the loads or lack of perfect uniformity of materials, varying dimensions of sections, residual stresses, end restraint variations, and other such issues. Because of these issues, we will not get the same dots on this curve, on the smooth curve, even if all the testing is done, all of the testing is done in the same laboratory. The usual practice is to attempt to develop formulas. Usual practice is to attempt to develop formulas that give results representative of an approximate average of the test results. The students should also recognize that laboratory conditions are not field conditions. You have to understand, like, laboratory conditions are not exactly the field conditions. Field conditions could vary compared to the laboratory conditions. And column tests probably give the limiting value of column strengths. The magnitude of the yield stress of the section, yield stresses of the sections tested are quite important for short columns, as their failure stresses are close to the yield stress. So for short columns, failure stresses are very close to the yield stress. For columns with intermediate slenderness ratios, the yielding stress are of lesser importance. One thing you have to understand, right? Columns with intermediate slenderness, the yielding stress is of lesser importance in the effect of failure stress, as they are of no significance for long slender columns. Especially for long slender columns, the yield stress does not have any significance. For intermediate range columns, residual stresses have more effect on results. So intermediate columns, the residual stresses will have more effect on the results, while failure stress for longer slender columns are very sensitive to support end conditions. Very sensitive to end support conditions. For longer columns, the failure stress is very much sensitive to the boundary conditions, end support conditions, in addition to residual stress and non-linearity. Okay. Let us see in these. So another dominant factor in its effect of column strength is member out of straightness. So this is one important factor. Member out of straightness. That's another dominant factor in its effect of column strength. So member out of roundness, out of straightness, it has impact on the column strength, right? Let us see here. Next page. The Euler formula. Let us study about this. So in this one, the Euler formula, we will talk about the Euler formula. Obviously, the stress at which a column buckle decreases. Stress at which column buckles decreases as the column becomes slender, longer. After it reaches a certain length, the stresses will have fallen to the proportional limit of steel. Will have fallen to the proportional limit. Suppose, for example, if it reaches certain length, then the stress at which it fails will have fallen below the proportional limit of the steel. For that length, greater length, the buckling stress will be elastic. So this is very important. For that length and greater length, the buckling stress will be elastic. So elastic buckling stress will be elastic. Okay, understand this buckling stress will be elastic. For a column to buckle elastically, it will have to be long and slender. So if the column is very long and slender, then only it can buckle elastically. Its buckling load P can be computed with the Euler formula. Pi squared EI by pi squared EI by L squared. This is the Euler formula for buckling load. This formula is usually written in a slightly different form that involves column slenderness ratio. Since R equal to square root of I by A, that's the radius of gyration. R equal to square root of I by A. We can say that I equal to AR squared, correct. Substituting this value into the Euler formula, P by A, if we calculate the stress, P by A, that means you have to divide by A right here. So pi squared EI by L by R whole squared will come. A L squared, we can find out by dividing both sides cross-sectional area. Pi squared E by L by R whole squared. That is the elastic stress. Okay, Fe. In the figure, we will see that application of Euler formula to a steel column. If the value obtained for a particular column exceeds the steel proportional limit, then elastic Euler formula is not applicable. So one thing you have to understand that when the elastic Euler formula is not applicable, if the value obtained for a particular column, pi squared A by L squared, if it exceeds the steel proportional limit, then that formula is not applicable. That let us see in the next. Here in this example, we can see that a column W10 by 22 is used as a 15 feet long pinned column. So it's a 15 feet long column, pinned column. Using the Euler expression, determine the column's critical buckling load. That's called pi squared A by L squared. We need to put. Assume that the steel has a proportional limit. That is this case a proportional limit. Repeat A if the length is changed to 8 feet, from 15 feet to 8 feet. Okay. So using 15 feet long, W 10 by 22 means that's cross-sectional area Rx, Ry. So minimum Ry we need to consider 1.33. So L by R, if you see it, 12 inch by foot, right? So 15 feet we are converting into inch, R is inch. So 135.3, that's the L by R. Elastic buckling stress is called pi squared EI by L squared, right? So this is the value L by R whole squared will come. Okay, so this is the elastic buckling stress. This elastic buckling stress 15.63, that is less than 36 KSI. So this is well within the elastic limit. So column is in elastic range, right? So the Euler formula is applicable. Euler buckling load equal to 15.63 KSI. That becomes with cross-sectional area we have to multiply, then 101 kips it will come. If it is 8 feet long instead of 15 feet long, almost half it's coming down. So this slenderness will be almost half, right? L by R 72. So pi square EI by this EI by LR square, if you put, then it becomes 54 KSI. That means that is more than elastic limit. So column is in inelastic range. It's not in elastic, it's in inelastic. The Euler equation is not applicable. Okay, Euler equation is not applicable if the column is in the inelastic range. That means the elastic stress or buckling stress is greater than the proportional limit of the steel. Okay. So here one more thing we need to understand. The students should carefully note that buckling load determined from the Euler formula is independent of the strength of steel. So it does not depend on the value of yield. It is independent of the strength of the steel. Euler formula. The students should carefully understand that the buckling load determined by Euler formula pi squared EI by L R squared, right? L by R whole squared. That's the formula. That does not depend upon the yield value. That's why they're saying that the students should carefully understand that. Note that buckling load determined by the Euler formula equation is independent of the strength of the steel. So Euler equation is useful only if the end support conditions are carefully considered. If end support conditions are carefully considered, the results continue obtained by the application of the formula to specific examples and compare with very well with the test results of a concentrically loaded. Long slender columns with pin ends. Designers, however, do not encounter the perfect columns of this type. I think they don't encounter the perfect column